Okay, hello, my name is Emmanuel. I'm one of Pat's chemistry academic coach. It's currently 11:31, but I just decided to make this video for chapter 13, which is alkynes. Um, so with this chapter, it's really similar to your previous chapter that you learned about alkenes. Alkynes and alkenes have very similar chemistry, and you'll just be learning like a bit of some new information, but the rest should be from Alkene chapter. I don't know how far Theodorakis goes in this, but if you need help, you can always ask me and come to my office hours. Um, but yeah, so let's start off with what are alkynes? So alkynes are carbons that are triple bonded to each other. These are alkynes. If you look at the chemistry, this carbon is sp2 hybridized. It has one sigma bond and then two pi bonds. And like I said, it has very similar properties with alkenes. The only difference might be their acidities and basicity. But again, I don't know how far he goes. I'm just trying to get by the basics right now. Um, so yeah, so I'll just jump right into the alkyne reactions. We don't really need to know how to name alkynes. We just need to understand their chemistry. So the first part is called reduction. It's reducing the alkyne down to something else. As you can see from our first reaction right here, we have an alkyne, just a simple alkyne. If we react it with, you've seen this before, hydrogen gas on a palladium and carbon, palladium on carbon, you get a full reduction to a alkane, which is very similar, if not the same as um, what it would be if this was an alkene. So this is just a reaction that you need to like remember, but it's very similar to alkenes. And then in the next one, we have this an alkyne again, but this time we're going to be reacting it with something different. This is called Lindlar's catalyst. So um, these reactions will sort of be focused on synthesis. So from this point on in organic chemistry, you're not really too worried about how reactions form. If you remember in 40A, you had to understand SN2, SN1, E1, E2, but now you're trying to incorporate all of that information and putting it onto a reaction, into a synthesis. So you'll be given like a starting compound, and then the synthesis would be like, I want you to make this compound from this compound, right? So you would have to know these reaction tools and mechanisms, not mechanisms, but reaction tools and reagents, so that you can prosper in these synthesis problems. So we have the first one is a full reduction, so it goes up to an alkane. But what if we don't want an alkene? What if we want to turn it into an alkene? So we would react it with something a little less strong than palladium on carbon. If you recall, palladium on carbon is really, really strong. So we use something called Lindlar's catalyst. And Lindlar's catalyst is a very, it's a least strong version of palladium on carbon. You can see we have palladium, lead, and then calcium carbonate with H2. And then this would give you an alkene. If you look at the R groups right here, they are now on the same side of each other, and we would call that a cis formation. So this makes cis alkenes. But let's say you don't want cis alkenes. Let's say you want trans alkenes. This is when we would use sodium on ammonia as a liquid. So sodium metal. If you use this, it brings you trans alkenes, right? Okay. Um, so these are just like the very basic of reduction with alkenes. And then now we'll go on to elongation of the alkyne chain. So what's really useful about alkynes is that this hydrogen right here, or this one, if it was a hydrogen, in this case it's an R group, this hydrogen is very acidic. If you remember in 40A, the trends of acidity, this is sp hybridized, so it has more S character. Therefore, this hydrogen is more acidic. And when I mean S character, I mean, let's take a look at sp3 versus sp2 versus sp. You can see there's only one S per 3 P's here, so it's a 1:3 ratio. But in this case, in an SP, it's a 1:1 ratio. So there's more S character. You can think of it, there's 25% here, right? 25 and then 75% of the P's. You can think of this as, what is that? Like 50%, I think. Oh no, this is the 50%, and then I don't know the, oh, this would be 33%, right? So if you think of it like that. So what we can do is we can react it with this reagent right here, sodium NaNH2. And what that does is it's a long and complicated synthesis, mechanism, but you need to know that it takes away this hydrogen and it creates um, a nucleophilic carbon. It's sort of similar to like a Grignard, very, very similar. But in this case, we have a nucleophilic carbon. And then what we can do is we can react it with a an alkane, a haloalkane with a good leaving group. And if you know about good leaving groups, you have a strong base, a strong nucleophile, you have a good electrophile in this, and a good leaving group. It's going to react in an SN2 fashion. It's going to be one step, and then you're going to elongate the alkyne chain, right? So if you take a look at this, I'm the carbon right here. I have lone pairs of electrons. My carbon here is delta positive because this is delta negative, right? X is a halogen. Um, so I can react it straight onto here, and then this leaves, and then now I'm left with an elongated alkyne chain, right? So let's take a look at this example right here of this synthesis type question. So I think I'm most definitely sure that like these types of questions will appear on midterms, but not this exact one, right? I'm just trying to see and gauge where you're all at. So I have here an alkyne, right? And then I want to have reagents here so that I can make this, okay? So the first thing I'm seeing is, well, first there's a double bond. So um, the alkyne turned into an alkene. And then I'm looking at, I added these groups right here, right? So I added more groups. Okay. I know a few reactions that helps me right here, right? I have the elongation, and these are trans to each other, right? So I have this catalyst. Okay, let's try to work this out, right? So we first have this compound, right? And then I wanna let's add this chain right here. Or we can add this chain. Let's add this chain up here, this ethyl chain, right? It's CH2, CH3. So if we want to add atoms, add things onto the alkyne, we first have to make it a nucleophile, right? And what made it a good nucleophile? This reagent right there, NaNH2. So let's add it with NaNH2, and then we form HC, this carbon nucleophile with a Na as a spectator in this process, right? Okay, so we can add whichever one we want. I'll just add this ethyl group first, right? So if I want to react this, I need to react it with a haloalkane, which is a good leaving group, right? So I need to add how many carbons? 1, 2. So I need to add CH3, CH2, and then let's pick a halogen. I'll pick bromine, right? Boom. So we have, this is very delta positive, this is delta negative because of the electronegativity difference. We can react it here. This bromine goes out. And then what do we make? HCC. We form 1, 2. So we add that onto our carbon. CH2, CH3. Okay, nice. So we have this part done, right? We have a CH3, CH2. But now I still want to make this part, right? And we have not only one, but we have 2 acidic hydrogens. So we can do this whole process again, right? Let's do the whole process again. Let me move this example down. Oops. Okay. Let me move the example down. Right. So we can do this whole process again because we have 2 acidic hydrogens. So let's do it again. HC, C, and then we added the ethyl group onto here, right? And then let's get rid of that acidic hydrogen by reacting with NaNH2. So we get C triple bonded to C, CH2, CH3. And then this is a nucleophile now, right? And then now let's focus on this part. I'm adding 1, 2, 3. I'm adding 3 alkanes onto that, 3 carbons onto it. So let's do that. Let's C, CH2, CH3, and I want 3 carbons, right? CH3, CH2, CH2, and let's stick with Br. Let me move this up here a little bit. And then let's nucleophile here. And then let's do the reaction mechanism. That attacks the C, this one goes out, and then we make, sorry, this is gonna be a little bit messy. We have CH3, CH2, CH2, C, C, and then I'll put it down here, CH2, CH3, right? So we created, now we have these 2 groups, right? So I'll show you what that looks like in a bond formation. So we have 3, 2, 3, and then we have the C right here. Oh no, 3, 1, 2, 3. We have the C, boom, and then we have there, right? But now we still want these 2 H's here, and notice that they're trans to each other, right? So what can we do to make it trans to each other? We have this reagent, Na sodium metal on ammonia, liquid ammonia. If we add that, then this turns into a trans alkene, right? And that finishes up our reaction. So plus Na liquid, Na solid on NH3 liquid. And then we're given this. The H's are on this side, and we have 1, 2, 3 carbons, and we have 2, right? So let's take a look at what we did again. Let's move this up a little bit. Okay, let's take a look at what we did. Okay, so first, I know that I have to add more bonds onto this alkyne. I have to add more bonds onto this alkyne, and I have to create a trans alkene. Okay, I know to make more bonds, I have to react it with this reagent, NaNH2. So we did that. Then we did an SN2 reaction right here with the ethyl, this part, with a halogen. I chose bromine. And then we got the first part of our product. But we also had another acidic hydrogen there. So we can do the same process again, but this time we're gonna add 1, 2, 3 carbons. Same process here. And then I was left with this. We're so close to the answer, but we just need to make this a double bond, and we need to make these groups trans to each other. And the way to do that, we learned up above here, is by a sodium metal on liquid ammonia. So we did that and we received this compound. Okay, I hope that's somewhat clear. And then now, these are just a few more reactions. I only have 2 more reactions, so I hope you can bear with me here. This one I have, it's a hydration of an alkene. It's a very long mechanism. The reason why I don't show it to you is because I never learned it, and I don't think you will learn it either. So what this does is it gives you your R groups, and then it makes this right here, which is called, you have an alkene, right? Alkene here, and alcohol. So chemists call it an enol, right? And this can actually turn into a ketone if you do something with this. If you move this over to this side and some base takes that hydrogen, it makes it a ketone, right? This will be important later on, but I just wanted to get you all used to it. And now we talked about alkynes to alkenes, but what about alkenes to alkynes, right? So we need to think of something that makes double bonds, and we need to think of something that does it fast. And if you remember how we made alkenes, the way was an E2 reaction. And I said before that alkynes have very similar chemistry to alkenes. So we can actually do the same thing. I'm just going to call this an R group because I'm really lazy to draw out the thing. But I have this, this reactant right here, the R group representing the benzene ring. If we react it with a dihalogen, right, if you remember, it forms something like this, where I have the Br here, C, and then the R group, and then the Br here, right? These have H's, something like that, right? And then notice that this is a stereocenter, and this is also a stereocenter. So we can actually do an E2 reaction with this, right? And an E2 reaction, you use a good base. So let's use, you can use any base that you want, but I find it easier to use something like NaNH2, which is a really good base. It's not as bulky, right? If you have bulky groups here, a base like tert butoxide might be a little iffy. So I think NaNH2 is a good bet. The negative is on the nitrogen. So if that reacts, if you remember the mechanism, these have to be trans to each other, sorry. If you remember the mechanism for this, oh wait, no, that was right, HBr. If you remember the mechanism for this, the leaving groups, which is Br in this case, and the hydrogen have to be anti to each other, right? And we have that here, so we can do this E2 reaction. So let me just show it once. This NH2 takes the hydrogen from the carbon-hydrogen bond goes to this carbon, and then the bromine leaves, right? So if we do that, we get R, C, double bonded to C, double bonded to R. We still have this bromine here, right? It didn't go away here. And then we still have the H right here, which didn't go away, right? So now we still have 2 trans groups on top of each other. We can then react it with another NaNH2, right? And then we can do the same thing again, where we take this H, this bond goes here, and then this kicks out the bromine. That leaves me with an R, C, triple bonded to C, and then an R. So we basically, I don't like using that word, but we pretty much did 2 separate, let me make this a little better here, that so I have more room to write like this. Okay, so we did 2 E2 reactions, which is why we formed this triple bonded alkyne from an alkene, right? If you remember the chemistry, an alkyne plus a dihalogen gives you uh, two bromines, and you can use this same thought process with alkynes. So um, yeah, so you would react it with the bromines. It would form this compound right here. You can do one E2 reaction. This is an 1E2 reaction. And this is another E2 reaction. And it gives you an alkyne. Okay. I hope that was able to help. I'm sorry if it confused you a bit more. I hope not. But if you have any questions, feel free to ask me. And make sure you keep up with the studies. And I hope you have a good weekend.